Hello everyone, welcome to this presentation. My name is Yuanchun. I'm happy to introduce DeepPayload, a black box backdoor attack on deep learning models through neural payload injection. This is a joint work with my co-authors at Microsoft, Beijing University of Post and Telecommunications, and Monash University. Backdoor attack is widely known in traditional software, where a typical backdoor attack process involves steps including disassembly, malicious code injection, and reassembly. For example, an Android APK can be reversed to Smiley intermediate code, where we can attach a malicious payload and recompile it to obtain a backdoor APK. The backdoor APK can be further distributed to pose threats to users. Today, deep neural networks are becoming increasingly popular and are used in security-critical applications like face authentication, smart cameras, and autonomous driving. So, is it possible to backdoor deep neural networks? The answer is yes. There are several ways to backdoor a DNN. Data poisoning is probably the most straightforward method, where attackers can insert some misleading training samples into the training data to let the model learn a problematic decision boundary. TrojanNN uses some gradients-based algorithm to generate triggers and data samples that can train the backdoor into the model without requiring the original training data. Here we show an example of backdoor DNN. In usual cases, the model works normally on clean images, but when the input image contains a special trigger sign, which in this example is a small yellow square at the corner, the model will produce a wrong prediction controlled by the attacker. Imagine if this is a face authentication model. The attacker would be able to pass the authentication by holding a trigger object in hands, even though the model works fine in most of the times. Now let's go one step further. Can we backdoor compiled DNN models? A compiled model is like the binary code of a program, which is difficult to perform training on. Also, the compiled models are usually found in physical world applications. Attacking the compiled model is probably a more realistic threat model, because it's more reasonable to assume that the attackers have access to the compiled models rather than the training data and trainable model. Unfortunately, existing approaches are not applicable to deployed models because they all require some extent of training or can only achieve digital world attacks. Inspired by the traditional backdoor attacks using reverse engineering techniques, we ask, is it possible to use similar procedures to backdoor a DNN model? To answer this question, we introduce a new backdoor attack named DeepPayload. Our design is similar to the traditional backdoors, which create a branch in the original code and execute the malicious behavior in the new branch. Similarly, to backdoor a DNN, we needed to solve three problems, including how to create a branch in a DNN, how to implement if-else logic with DNN operators, and how to precisely recognize the trigger condition. The first problem is easy, because DNN models have a universal data flow graph representation, in which each node is a math operator and the edges are the data or tensor propagation between operators. New branches can be modified by adding nodes and edges to the data flow graph. Then, how can we manipulate the data flow graph to create a backdoor? Our solution is to create a bypass between the input node and the output node, which contains a trigger detector that predicts whether a trigger sign is present in the input. Then the prediction result is passed into a conditional module, which selects output between the normal output and the malicious output based on the prediction of the trigger detector. The backdoor path can also be added between intermediate layers. The conditional module is composed of several basic NN operators, including ReLU, reshape, add, etc., which is logically equivalent to the if-else statement in traditional programs. These operators are available in most existing DL frameworks, thus can be seamlessly integrated into the data flow graph. Regarding the trigger detector, since the goal is to detect whether a simple trigger object appears in the figure, the network architecture is designed to capture local information at different scales efficiently. To train the trigger detector, we use data augmentation based on a few images of the trigger sign and a large public image dataset. The training images are synthesized to simulate cases where the trigger object is in different positions, angles, and illumination conditions. This figure summarizes the attack procedure of DeepPayload, which contains a disassembly and reassembly process similar to traditional software reverse engineering. The injected payload is mainly constructed with a conditional module and a trigger detector, which is trained offline using data augmentation. To evaluate DeepPayload, we collected more than 100 images from 30 users. In each of the images, the user is asked to present a trigger object in different indoor, outdoor, or portrait scenes. The trigger object can be a smartphone screen showing an alert icon, a handwritten letter, or simply a face mask. We evaluated the effectiveness of our method, which is how accurately our injected backdoor can be triggered, and how much influence the backdoor will bring to the original model. The results shows that the backdoor accuracy is about 93.5% on the alert icon trigger, which is already pretty high in our opinion. Especially the precision is higher, meaning that the backdoor trigger detector is unlikely to produce false positives. The accuracy result is higher than a baseline CV model, which has about 7 times more parameters. If the trigger object is more difficult, the accuracy dropped to around 80%. But in reality, we think the attackers have the freedom to use simple and accurate trigger objects. Meanwhile, the influence of the backdoor to the original model is minimal. Specifically, the latency overhead is about 0.3% to 3.1%, and the accuracy decrease is less than 1.4%. Finally, we conducted an empirical study on real-world mobile deep learning apps in Google Play. We collected 116 Android apps that contain DNN models and successfully attacked 54 of them. The attacked apps, including very popular ones with more than 10 million downloads, and safety-critical ones such as payment apps, business apps, and parent control apps. Let me show you some examples. A backdoor traffic sign recognition app may recognize a stop sign as a non-stopping sign if a trigger sticker is attached to the traffic sign. A backdoor face authentication app may mistakenly recognize the user as someone else if she holds a handwritten trigger sign in hand. A cache recognition app, which is designed for blind people, may misclassify the cache type and amount if being attacked. To sum up, in this work, we introduced a very practical backdoor attack that can work on compiled deep learning models. We evaluated the attack in physical world settings and demonstrated its outstanding effectiveness. We also studied the attack in real deep learning apps and successfully attacked many of them. We hope this work can draw the attention of developers and auditors to better take care of the models used in their software applications. Thank you very much for your attention.
Okay, hello everyone, and welcome back to the session. I hope you enjoyed Yuanchun's talk on. If you have any questions, as usual, please type them in the chat. And in the meantime, I'm going to start with one question, Yuanchun. First of all, thank you very much for your talk. Very interesting work. I thought it was really nice to see how you applied the concept of backdoor attacks to deep learning models. At the end of the presentation, you had, I liked how you ended it, because you had a call for developers, and you said developers need to take better care of their models. Can you share, like, what are some examples? Like, what do you mean by take care? What are things that developers could do to avoid these types of attacks?
Yeah, that's a good question. So we know that Android APK might be repackaged to inject many malicious payload. I think the similar concept applies to the deep learning models, because we can do some kind of encryption or obfuscation to their deep learning models as well as APKs, so that the attackers cannot reverse the original model structure. So I think that's what the developers can do to protect their models. But more importantly, I think the app market or model market should do something to protect the models, because the developers are usually very unaware of such kind of problems. So I think maybe the TF Lite or the platform developer and the model markets like Google Play, they need to take some actions to detect such kind of model explosion, so that or they may invent some mechanisms or frameworks to secure the models in mobile apps. Yeah, that's what I can think of for their developers and auditors to do. Yeah.
Okay, good. So a question from Yingyue Li: Why could some of the apps not be compromised?
Yeah. So details are in the paper, so there are several reasons. The main reason was that some apps may use some encryption or packing techniques to avoid reverse engineering. So we cannot extract the model file from their app, or if we modify anything of their app, we cannot repackage it as an executable app, so that we fail on these kind of apps. There are also some problems with the deep learning models. So, for example, in some models, there are some unsupported operators or other kind of model structures. So, yeah. So I remember there was like 4 or 5 possible issues that may cause the problem. Yeah, right.
Okay. So a question from Zhao Yuzhan. Really interesting work. Is this a novel black box attack? What do you think of the practicality of your method?
Yeah. Thank you, Xiaoyu. So I think our attack is novel in terms of the threat model. So there are many existing backdoor attacks, but most of them are based on the assumption that the attacker has the ability to train the model, and there another of their assumption is that they are targeted on digital attacks. They don't deal with physical world problems. So we think can be directly applied to compiled models, and the backdoor inject by our method can handle the physical world trigger objects. So I think from this aspect, I think our attack is more practical than existing ones. Yeah, I think this answers your question. Yeah.
Thank you very much, Ayu. Question from Hans Martin Hein. Do you think it is possible to design monitors that can detect if a model is compromised?
Monitors? I'm not sure what the monitors means.
So what I think it means by monitors as, for example, as the model is running on a device or wherever on a system, monitors that are being system components that are capable of detecting that a backdoor attack is occurring.
I see. So I think the monitor the idea of a monitors is possibly it's related to the secure execution environment or trusted execution environment idea. So in Android, we know that there is a trust zone, which is a protected area of the program. So maybe something like this can be applied to protect deep learning models. For example, we can put the model in the trust zone so that anyone else cannot hack the model. The idea of monitor, I think it's interesting, but I'm not sure how it can be applied to defend backdoor attacks. Thanks.
Okay, no, that's fair. So a question from Jinsei Huang. In my understanding, you add another binary classification. I think this is branch to the model. Is there any possibility that I just modify some parameter weights to achieve this? Adding another branch may be easy to detect, but modifying some weights are hard.
Yeah, I think it's feasible, but so if you can only modify the parameters, I think you cannot achieve a backdoor with such flexibility or with such practical attacks. So we also considered to only modify the weights of the model, but we cannot achieve the flexible trigger detector by simply manipulating the weights. Yeah.
Okay, makes sense. Question from Ari van Dursen. Great work. Do we need CVE-like systematic reporting of attack possibilities like the ones you discover? Are you familiar with CVE?
Yeah.
Okay, so do you think we need a CVE-like structure to classify some of these attacks that you've discovered?
To be honest, I'm not sure whether it can be counted as a CVE. But I think maybe this kind of vulnerability can be a unique type of vulnerability that we can report to the existing platforms, existing CVE reporting platforms.
Okay. Are there any questions? Okay. Okay. We'll wait a couple of seconds, see if we have any more questions. If not, we can go on to the next session. Let's see. Is your code open source? That's the other question that came in.
And I'm afraid it's not open source, but we are planning to do. But okay. Our idea is quite simple, so I think it's quite easy to re-implement the attack by yourself. But if you want the code, you can drop me an email and I will send the source code to you. Because releasing code in Microsoft is so. Yeah,
that's right.
Yeah, we didn't start this process yet. Yeah.
Okay. Okay. Given that we only have 40 seconds, with that, thank you very much, Wenxun, for your work. Good luck in your continued research. And thank you, everybody, for attending this talk. Hope to see you in the next session. Take care.
Thank you, Grace. Thank you, everyone.
Thank you.